Well, hey everyone, welcome back. This is part 2 of the 5 transistor amplifier. Trying to make a amplifier. Like to get 2, maybe 2.5 watts of output into 4 ohm loads. And if you watched the last video, I concluded that I don't really have enough drive current for the transistors. The output transistors may not have enough gain, so I'm going to set up a little circuit and test their gain, measure their gain, and compare them with some stronger transistors to see if they have better gain, and we'll go from there. Also need to make sure I have enough drive current, and this transistor here pretty much drives the output. Now I should reinforce what I said initially in the last video. This is going to be a simple amp. It's not going to have a lot of extra parts. Got to be done with 5 transistors. So I'm not going to add any current sources or extra stages. So what happens is this amplifier needs to do a lot to get the current high enough. So we're calling on the earlier stages to have a little bit more current in order to drive these outputs, since we don't have drivers on the output transistors. So as you put a heavier load, this transistor needs to have more current in this part of the circuit, and even a little more current in the input stage to drive this transistor. So the heavy load kind of reflects itself on the previous stages. Negative feedback also plays a part in that when the output is loaded down, it creates a larger error signal that these earlier stages have to be pushed harder to correct that error. So I need to look at these earlier stages, make sure I'm getting enough current out of them. I did look at the differential pair here and adjust these resistors, try different values, and it seems to be good as I originally had it, with 1K here, 1K here. So I'm going to move on to this second stage. This is the voltage gain stage, also known as a Class A transistor. It's a driver too, because in this amplifier there are no drivers for the output, so it's directly driving the outputs. So I need to take the output stage away. So this is what I've done. I've taken the output stage off and connected this Class A driver here to the positive rail through a load resistor, and I connected the negative feedback to this point, or it's not going to work. And I'm just checking the distortion and seeing how this transistor deals with the different loads I put on it. So let's take a look and see what's going on. Okay, here is the amplifier again. This is the differential pair. This is the voltage gain stage, and it comes out over here. The output transistors are removed, and in fact this whole circuit is just going to this resistor to the positive rail. None of this is connected at the moment. And I'm looking at the output, and you can see, if I adjust it, there's clipping. I'll dial that back. Let's turn this off and look at the FFT. See, it really, the harmonic spikes really grow when we get into clipping. But out of clipping, it's not too bad. You see, here is our 1 kilohertz fundamental, and it's 1 kilohertz per division, so 2, 3, this little spike at 3, 4, tiniest little blob at 5, and out here there's a couple. But you see this spike here, it's in between the natural harmonic points. In fact, that's at 4.5 kilohertz. Now that is my doing. What I did is I made a waveform. I added a signal at 4.5 kilohertz, and I made it 1% of the fundamental. So what you're looking at here is what a 1% distortion is. I made it non-harmonically related so it wouldn't interfere with seeing the harmonic nodes around it. I can see the amplitude of the other harmonic peaks relative to my 1%. So this is not really bad, but we have only 1 kilohertz resistor, load resistor connected. Now I'm going to connect 150 ohm, and look what happens. Something weird just happened. Well, you see the distortion has increased. Let me make sure. Now there's clipping. I want to make sure we're not clipping. So now you can see our second harmonic has really shot up well above our 1% level. That's like a 2% distortion. The third harmonic is pretty high. It's almost equal. And then there's the fourth and fifth. No sixth, but a little bit of a seventh. So loading down the driver transistor really kicks up the distortion. But the good thing is the transistor is driving it okay to the rails, but we're just pushing it too much. Yes, you can feel the heat here. This transistor, this driver gets warm. It's not hot, but it is quite warm. See, and just before clipping we have 4.05, we'll just say 4 volts RMS going into a load over here. It's 150 ohm in parallel with the 1000 ohm. So, I've calculated that already. So that's equal to about 130 ohms. So if we put 4 divided by 130, and we're pushing about 31 milliamps RMS. So it's doing the business, but however, that distortion is what bothers me. I'm going to try a stronger transistor here, because when you're driving a transistor hard enough, that it doesn't seem like that's a lot of current. However, now we have to look at the peak values also. This is a class A driver stage, and it's peak to peak, this is 2 volts per division, and it's almost 12 volts. So it's pretty much pulling, as it pulls the signal down to the negative peak, it's pulling pretty much the supply rail through that load, and it on the upswing at the top almost no current flows because it's almost at the supply rail. So if you got 12 volts through 130 ohms, that's almost 100. Well, it's like 92 milliamps, but we're getting close to 100 milliamps for that transistor to be working with. And going from 0 to that much current in a small transistor, it's going to cause a lot of distortion. So let me flip this. Oops, turn this off. See if we can get rid of some of that distortion there. That's, it's back it away from clipping a little bit. This is about what we're getting. Quite a bit over 1%. So see what we can do to correct that by adding a better transistor. Okay, so I replaced the little 2N3904 with the BD139, which makes more sense because it is driving the outputs directly. Doesn't get nearly as hot. And let me adjust We're getting a larger signal before clipping even. That's good. Let me turn off the waveform. And look at that. Distortion is much lower. Well, that's clipping. Much better. It's kind of weird. Our second harmonic is gone. We have a little bit of third harmonic. So my built-in notch, you can see that our distortions are much less than that now. So, and the vertical scale is linear, by the way, so you can call that around a little more than half, like 0.6% of the fundamental. So just changing that transistor made a huge world of difference there. Not perfect. I mean, we are still driving quite a load. Now we're going to take a look at the output transistors. So I set up a little measuring jig so I can measure the current gain of these transistors. And we'll start with the original outputs I was using, the BD 139 and 140. And if you remember from the last video, the datasheet said the current gain drops to as low as 25 with half an amp of collector current. And that's pretty low. You know, they probably won't be that low. I don't know. You see, we needed a lot more current. We needed like 1.2 amps, if I remember correctly. The gain can drop as low or even lower depending on these transistors. So I want to measure that using this jig. And I have these. These are the only transistors I have, you know, in complementary NPNs and PNPs. And we'll try those and see how they work in the circuit. Well, here's the circuit for checking the gain of the power transistors. I have an amp meter in the collector circuit, and this resistor here in the emitter circuit, and I'll talk about that momentarily, and a voltage source here, adjustable, and a resistor here. And instead of putting a amp meter in line here in series, I'm just going to measure across this 100 ohm resistor. For every volt drop across this resistor is 1 milliamp, or I'm sorry, 10 milliamps of difference. So, you know, I can just use a voltmeter and measure across the resistor there. Now, you see this resistor here, you might say, isn't that going to affect your gain measurement? Well, not really. It will affect the voltage I have to put into this thing, you know, as I adjust it. It also makes it easier to, you know, adjust the voltage. It's not going to be as touchy. But it does not affect the gain measurement of this transistor. You're still going to have to put X amount of current in to get X amount of current to flow in the collector there. Okay, so here it is. We'll test this BD 139, and this meter is across the 100 ohm resistor, and the clamp meter is, well, I have it on the power supply lead there, which goes to the collector. And I'll turn on the supply, and I'll bring up the voltage here. We're almost at, yeah, that's about 1 amp right there. 1.8 is the voltage across. So that translates to 18 milliamps. So now we can calculate the gain. So it's 1 divided by 0.018. So our transistor has a gain of 55, which is better than the data sheet. course, on the data sheet, like I said, it was in the minimum column. That'd be the minimum gain. And yes, I'd have to test a whole bunch of these transistors because they will vary in gain. That's just the, the nature of the beast. But they are better, but not really as good as I would want. It does make it harder though, because I doubt these transistors are going to be too much better. They might be around 100, but it would be nice if they were more. So let me hook these up and get a measurement from them. Okay, got this transistor here. It's a equivalent to a 2SA 5200. They call it something a little different because it's in a TO220 package. Same power transistor die, just derated for power dissipation because the smaller TO220 package. But, like I said, those are the only ones I have in complementary pairs to use in the circuit. So, fire this up and adjust until we get 1 amp. Oh, a little bit high there. That's close enough. And about 1.09 volts across that. So that's 10.09 milliamps of current. So let's do the math. Okay, so it was 1 divided by 0.01. We'll just say 1. It was close enough. So that transistor has a gain of about 91. 91, so yeah, they are better, but they're not hugely better than the other ones. But that'll work. We'll try them out in the amplifier. A little bit gain would be nice. A surplus of gain would be great, because that means the driver stages previous to the outputs will not have to push them so hard. But, well, we're not going to get that, so we'll just see how this thing performs. Okay, I have the new transistors in. Now, for some reason, they flip-flop the base emitters, so I have to put them in backwards from normal. Otherwise, I have to rewire all of that mess. And here is our output. This is 8 ohms. You see our 1% reference notch there. The distortion is less than that. And we start to clip right around there. And we're getting about 2.85 volts. Non-symmetric clipping. So our circuit still has an issue. And it's clipping on the top. I think our bootstrap is not working well for us. Let me see here with the meter. See your supply voltage. I don't know if I can get that in the shot or not. Well, you just have to trust me. Let's see, our supply voltage is should be 12.6. Wrong setting. Ah, these wires in the way. 12.6 volts. And our output, if I can get the meter in there, I don't short anything, I can put it here. 6.06, it's pretty close. We got a hungry kitty. I think our bootstrap current source is not providing enough current for the upper transistor. So I'll have to tinker with that and see if I can improve that. Okay, well, I got the abomination working. And We'll check here if it meets its goal. And I think it does. Well, I had 510 ohm resistors on each value up here in the bootstrap circuit. Well, that's obviously too high. So I changed them to 100. That's more in line with the load that I was putting on this transistor when I was doing that test without the output stage earlier. And plus having the bootstrap capacitor there, it should really improve it beyond that. Now when I increase that load, the DC current now flowing through the bias part was turning these transistors on to like 500 milliamps, which is way too much. So I had to remove one of the diodes and add a 6.8 ohm resistor. Now that might throw my thermal stability to the wind, but it doesn't. Three things are important for your thermal stability. One is your heat sinking. You have to have a big enough heat sink. Two are your emitter resistors. Three is your diodes here. They really should be mounted on the heat sink. I cannot do that on this breadboard very easily, but I do have it next to the leg, so it does get some heat. And this circuit has been turned on for half an hour, putting an output signal out full before clipping output signal. And these heat sinks are just, they're warm, not very warm. I mean, they're probably like 100 degrees, whatever that is, and that's Fahrenheit, whatever that is in Celsius. I stopped the signal, we dropped down. We're running about 13 milliamps of bias current, and it doesn't jump up or anything. So this thing is thermally stable. So that's another important thing. Now we got all that solved. I got the 4 ohm loads hooked up. They're both getting a little warm. This thing's been running for a while, like I said. Okay, let me turn it up into clipping. You see the bottom starts to clip first. That tells me the bootstrap circuit is definitely working. So that's excellent. And I'm not worried about the bottom clipping earlier. Right? I got as much current out of that transistor as I'm going to get, I think. So if I turn, let's turn this off. And here's my built-in spike that's built into the original signal, the input signal. So like I said, the amplifier is not producing that. That's clipping. And we'll turn that out. Let me tune the other harmonics out. Probably about as low as we're going to get. You know, that's our highest peak. Let's turn that on so we can get a voltage reading. So we're running at 3.33 volts. RMS into 4 ohm loads. And I already know that's more than 2 watts. Okay, 3.33 squared. Divide that by 4 ohms. 2.77 watts. Almost 2.8 watts. At 12.6 volts into 4 ohm loads. Under 1% total harmonic distortion. Bingo. The little amp on the breadboard here has met its objective. Thermally stable as well. Doesn't seem to have any oscillations or anything like that. So here's the complete circuit. In the other video, I had this backwards. Nobody mentioned it, but oh well. So I think I have everything drawn out correctly. Almost forgot to give you a quick listen here. Well, I only have an 8 ohm speaker, so I'll just leave one of the 8 ohm loads connected. And here's what it sounds like. Okay. That was fun. Thanks for watching. Have a good one.